All right. Hello, everyone. We're going to go ahead and get started. Today, I have the pleasure of introducing Berthy Feng, a new IAIFI Antibody Fellow here at MIT. Berthy develops data-driven and physics-informed priors for ill-posed inverse problems, taking insights from computer vision. And her work has applications in astrophysics and in medicine. Berthy obtained her PhD at Caltech, where she worked with Professor Katie Bauman on, among other things, black hole image reconstruction with the Event Horizon Telescope. And today she's going to tell us a little bit about some of that work.
Thank you for that very eloquent introduction, Alex. So yeah, as Alex said, I'm a new IAIFI fellow here, and I'm excited to share the previous research that I've done as well as current research that I'm interested in. And then towards the end of the talk, I'm going to share some broad directions of future research that I'm interested in pursuing. And since I am new here, I'm still meeting everyone in this community. And so please reach out if you find any of these topics interested and would be open to collaborating. So today I'll talk about advancing scientific computational computing through using both data-driven priors and physics-based priors. I'm wondering if I kind of want to get rid of this annoying cursor here. Maybe if okay, that's good. Yeah. Okay. Is that okay? Okay. All right. So, as many of you may know, in 2019, the Event Horizon Telescope, or the EHT, gave us the first ever picture of a black hole. So this picture advanced science by showing a result consistent with Einstein's theory of relativity, and it pushed the frontier of what people imagined could be possible to image. Despite all that, people couldn't help but comment on the appearance of the picture. And you have to admit that it is kind of blurry, right? And probably the reason that we think it's blurry is because we're used to seeing these very rich graphic simulations of black holes. And so the visceral reaction that people had to the real M87 picture reflects that many of us carry our own assumptions or priors of what we expect to see, and that often means wanting to see even more than what the telescope data can provide. But just taking a step back for a second, seeing M87 was an impressive feat of computational imaging. It started with a global array of radio telescopes organized by the EHT, and that alone wasn't enough. The EHT had to use computational algorithms to transform the raw telescope data into an interpretable image. And this image is blurry. Yeah, I was hearing an echo. This image is blurry because it's at the intrinsic resolution of the telescopes. And the EHT understandably didn't want to enforce strong assumptions beyond simple priors like spatial smoothness and compactness so that we could let the data come through in the image as much as possible. But going forward, we can use more advanced algorithms and even stronger assumptions to get richer images and even videos. And this idea applies not just to astronomical imaging, but to other domains as well, like in medical imaging, where we might want to go beyond static MRI scans to dynamic ones. In microscopy, we're starting to resolve 3D protein structure, but we still want to look at an even more complex system of molecular dynamics. And in all of these settings, there's always more that we could want to see. So in all of these settings, there's always space for imposing stronger assumptions in the imaging process. So we can think of this as moving along a spectrum of increasing imaging complexity, going from more sophisticated 2D image reconstruction to dynamic 2D imaging, and even to dynamic 3D imaging. Now, as the imaging problem becomes more complex, that typically means that we have fewer constraining measurements when solving the inverse problem of imaging. And so we have to incorporate additional assumptions or priors in order to fill in the missing information that the data can't provide. So there's a direct correspondence between the strength of the imaging assumptions that are needed and the complexity of the problem itself. And in my work, I further kind of delineate this into data-driven priors and physics-based priors, where I like to think of data-driven priors as slightly less strong than physics-based priors because they incorporate the statistics of large-scale data sets and tend to be more flexible than physics-based priors, which are rooted in strict physics equations and models. So in my work, we've tackled different problems along the spectrum, specifically in black hole imaging. So today I'll talk about our line of work on score-based priors, where we use score-based diffusion models as priors in Bayesian inference of an image posterior given EHT data. So we applied this to the real EHT measurements of M87. And recently we proposed video diffusion priors for solving the dynamic imaging problem. And currently we're working on performing dynamic emission tomography of the 3D fluid flow around a black hole given EHT measurements from Earth. So this is single viewpoint 4D tomography, which is a very under-constrained problem, and that's why we need to incorporate physics knowledge. Now, it would be beneficial to merge these two paradigms of data-driven and physics-based approaches so that whenever we use a data-driven prior, we can trust that it does satisfy known physics constraints. For that, we recently proposed a method to incorporate arbitrary constraints in a flexible manner into generative models such as diffusion models. So I'll talk about all of these different topics throughout the talk today. So let's start with scaling up the complexity of 2D static and dynamic imaging by leveraging recent advances in generative AI. The motivation is that we wanted to offer a way to see beyond the blur of the original M87 image by plugging in different, potentially stronger image assumptions. What if, for example, we assumed that this image came from a black hole fluid flow simulation? Or what if we assumed that it was like a generic natural object that you might just sample from Earth? We could even ask ridiculous questions like, what would M87 look like if it were a person's face? And it kind of looks like a scary Phantom of the Opera situation going on. So to flexibly incorporate different image assumptions, we turn to diffusion models as data-driven image priors, specifically score-based diffusion models, which are state of the art in generative modeling nowadays of images. But for the purposes of this talk, you can think of a score-based diffusion model as just a black box, which, given a training data set of images, learns to generate new images that resemble the data distribution of the training data. So once its weights theta are learned, it defines a learned image distribution, which we would like to use as a prior distribution when solving the image reconstruction problem. And the nice thing about diffusion models is that they're fully probabilistic, meaning that you can evaluate probabilities of images under the learned prior. For in-distribution images, we expect the log probability to be high, and for out-of-distribution images and images of pure noise, the log prior probability should be lower. And when it comes to image reconstruction, the goal is that we want to find images that maximize agreement with the observed data as well as likelihood under the prior. And so we can think of this as an optimization problem over the image X. And we want to maximize the log posterior probability of the image X conditioned on the measurements Y. And by Bayes' rule, we can decompose this objective into a likelihood term, log p of y given x, and a prior term, log p theta given x. So the measurement likelihood incorporates the sensing system, right? It says that for a proposed image X, if I were to observe it with my telescopes, then I would get a set of measurements y hat that should agree with the actually observed measurements y. Whereas the prior incorporates the learned prior of the diffusion model and is agnostic to the particular imaging task at hand. So in our previous work, we showed that you can actually use the exact log probability function of a diffusion model for this, but it turns out that that's quite computationally expensive. So in follow-up work, we proposed an efficient surrogate. So we proposed using the evidence lower bound or elbow of the score-based diffusion model, which is computationally more efficient and results in almost as accurate image posteriors. So yeah, it was easier to introduce things in terms of reconstructing a single image, but I've been talking about estimating a whole posterior distribution of images. So to do that, we actually solved this optimization problem where we parameterize the posterior using a generative network Q with weights phi. And the goal is to minimize the KL divergence from Q phi to the target posterior. And then once we solve this optimization problem, then we can sample from Q phi as a posterior that's close to the true posterior in a KL sense. Okay, so as I teased earlier in this talk, we applied this method to reimagine the M87 black hole from real EHT data. For reference, here's the image given by the EHT in 2019. And we applied a bunch of different score-based priors trained on different data sets. So one of those was trained on the CFAR10 data set of generic natural images. This would be sort of our simple prior. It would represent generic natural image statistics. We also applied a prior trained on the Celeb data set of human faces. We applied a prior trained on simulations under a model known as GRMHD. And finally, the strongest prior we looked at was trained on images under a geometric model of black holes known as RIAF. And this is constraining because it parameterizes the image as just a ring with a certain size and brightness profile. So there aren't a lot of free parameters there. And as I mentioned, we reconstruct not just a single image, but an entire distribution that we can sample from. So that allows us to get some notion of uncertainty. So to do that, we simply took the pixel Y standard deviation of samples from our estimated posteriors. And the one thing I want to draw your attention to is that as we go from left to right and the image and the priors become stronger in the strength of the assumptions, then the magnitude of the standard deviation also goes down, reflecting overall less uncertainty with a stronger prior. When it comes to the images themselves, I want to highlight that all of these images satisfy the same underlying data, and the only thing that's changing is the prior that's being used. So the benefit of using diffusion models for this was that we were able to flexibly impose different assumptions simply by changing the training data set of the diffusion model, whereas previously with simple regularizers like the ones used by the EHT, it would have been infeasible to write down analytical regularizers to represent such a large variety of priors. And then even though these images look different, there are still some characteristics that are shared regardless of the prior, such as the appearance of a ring, which is crucial, the diameter of the ring, as well as the location of the bright spot, which is sort of in the lower left corner of the image. Everything else, though, is up to the prior's interpretation. So, for instance, under the GRMHD prior, we get this thin ring with gas swirling around the shadow of the black hole. And remarkably, under the face prior, we still recover a ring shape, although it chooses to explain the ring in its own creative way, like using facial features like an eyebrow, cheekbone, and a nose. So we also recently tackled the more ill-posed problem of reconstructing dynamic images of black holes, i.e. videos, from EHT measurements by using video diffusion models. So for this example, we actually simulated EHT measurements of a black hole that evolves much more quickly than M87. So the ground truth is shown on the left, and then our reconstruction is shown in the middle. The baseline approach that was used before our approach was basically training an image diffusion model on static images and then stitching together those images using simple temporal regularization. Whereas with our approach, we learn both the spatial and temporal priors directly through the video diffusion model, and then plug that video diffusion prior into any off-the-shelf diffusion-based inverse solver. And the key contribution of our approach is showing that it is actually computationally efficient to train a video diffusion model and plug that into an inverse solver. Another cool thing is that our method is able to recover multiple modes in the posterior. So in this case, the ground truth is spinning in a certain direction, but our results showed two modes, one of which was spinning in the same direction as the ground truth, but this mode is actually spinning in the opposite direction. And it turns out that it's equally likely under the measured data. Yes. Tess? Yeah.
Hi, sorry for that. I just had a quick question. I think I just missed something.
Okay.
When you're going about generating something and your target is to something that matches as close as possible, given your priors to the ground truth, how are you conditioning the model to generate that specific thing?
So we're conditioning it on just the simulated EHT measurements.
Okay, so just the measurements.
Just the measurements.
Okay.
Yeah.
And then I know you're for the previous case, you were saying there's different data sets for sampling different priors. Is the conditioning different in that case?
So the conditioning is the same. It's just that the pre-trained diffusion model was trained on a different data set.
And so then if you are taking the EHT data, are you figuring out what part in the sampleable latent space it should lie for generation, or?
Like how are we actually choosing the prior? Is that kind of how you?
I guess I'm imagining for the prior, you
Yeah.
don't have a data that is commensurate. So how
Yeah.
do you kind of stitch the fact that you have a generator that has a prior of a certain data set that's trained to match a certain prior versus training something that is taking external data, which is physics.
Yeah.
Yeah. So I think I missed how those get stitched together, if that makes sense.
Yeah. So if I understand correctly, the question is sort of like what happens if you have a mismatched prior? Like,
No.
like how do you?
I can ask after. I can ask after.
Okay. Sorry. Okay. I mean, I can also spend more time on this because I feel like it's important if other people had the same question. Yeah. Yeah.
Oh, thanks. So from my understanding, you have a prior, which is a diffusion model.
Yeah.
Trained on some images, and you have a likelihood, and that's coming from the data from the observation, right?
Yes.
I think the question is, how is the likelihood injected into the prior? Are you fine tuning? Are you training another model entirely? Like, how are you going from prior model, which doesn't know the data, to posterior model, which knows the likelihood?
Oh, yeah. Okay. So they're basically, just think of them as like two separate modules. Like they don't really like talk to each other besides in the posterior inference step. So, yeah. Okay, maybe I like this. So yeah, we really do just decompose the posterior into like two distinct terms. So we separate them out so that the prior doesn't have to talk to the measurement likelihood at all. So what's happening is that like when we model the posterior, when we sample from our posterior, we kind of evaluate this term, which is its likelihood under the measurements. And then separately, we evaluate the likelihood under the prior. So there's no kind of crosstalk between these two terms. It's just that we minimize the sum of these two terms. Does that answer your question? Okay.
I have one more small question. So yeah, I get it for variational inference. Are you also able to generate samples in the posterior, or is that a separate task?
So once we fit the variational distribution, this Q-Phi network is a generative network. So we sample from that. Yeah. So this is I don't know if you're like familiar with other diffusion model literature, but this is kind of fundamentally different from the way that diffusion models are typically used for inverse problems, which is that so you pre-train your diffusion model and then you have this like reverse diffusion process to generate images from the diffusion model. And then you kind of like incorporate your measurements somehow as a conditioning step in the sampling process. Whereas this is just like fundamentally different. The thing that we're sampling from is actually like a separate network that's optimized to approximate the posterior. Yes, Eric. Okay.
Is there a reason why adding the conditional in the actual sampling from the you can add in control during the sampling process on your diffusion model, right? Is there a reason why that doesn't work? It seems like that would be a little easier to do than trying to do the variational inference.
Yeah, I love that question. So it is easier. It is typically faster to do that if you just like condition your diffusion sampler on the measurements. But the issue is that you're not guaranteed an exact posterior. So the way that the diffusion model sampling works is that you have to heavily approximate the way that the measurement likelihood term looks at the different noise levels. And then what that results in is having a final distribution that is really not close to a true posterior at all. It really looks more like a conditional distribution rather than a true posterior. So with this formulation, you have more control over how exact your posterior inference is. So like how exact your posterior inference is really just boils down to how expressive your Q-phi network is. And assuming that your optimization has worked perfectly, and assuming you have an infinitely expressive variational distribution, then you can exactly cover the true posterior. Yeah, but whereas with if you do what Erica was saying with like conditioning your diffusion model on the measurements, then yeah, very unlikely that you would get a true posterior. Yeah. And another difference is that this is hyperparameter free. So like with a lot of the diffusion model sampling based methods, you have to like tune like a hyperparameter in the process. This is getting into the weeds a little bit, but with this, you don't really have a hyperparameter. Yeah. Okay, yeah, thank you for the questions. Please let me know if anything is unclear at any point. So I'm just gonna jump ahead. Cool. So yeah, that kind of wraps up our discussion on the whole posterior estimation of images section of the talk. And then now I want to talk about a problem that I'm currently working on, which is reconstructing the dynamic 3D fluid flow around the black hole, given EHT measurements taken from Earth. So more formally, the task here is to go from like, say, a video of emission around the black hole. Say we've reconstructed a video of the black hole. How do we reconstruct the dynamic fluid flow around the black hole in 3D that when projected onto the image plane would agree with the observed video? And this is essentially like a 4D tomography problem, which is different in many regards from traditional tomography problems, such as in computed tomography and 3D scene reconstruction, where we typically assume a static source and multiple viewpoints. In our case, we have an evolving source, so we can't simply aggregate measurements across time for the same object. We have a single viewpoint, which limits the amount of 3D information that we can recover. And also, in our setting, light doesn't follow straight paths. It follows these curved geodesics as a result of the warping of space-time caused by the black hole. And so with these challenges, our problem is extremely ill-posed, meaning that there are infinitely many possible 4D reconstructions given the same observed video. To further narrow down the solution space, we propose incorporating physics into our approach. So we jointly estimate a velocity field along with the emissivity field. And then this velocity field informs the dynamics of the estimated emissivity, as well as getting incorporated into the image formation model. So the first ingredient of our approach is how to actually represent the volume. So let's say that we have like a 3D volume at time t of the emissivity. So we use a coordinate-based approach where for every position, we query an MLP to output the scalar emissivity at that point. So the input would be the 3D spatial location concatenated with the time, and the output would be the emissivity at that point in time. And then for the velocity field, we represent it very similarly, only we assume it doesn't change with time. So we represent it as a 3D MLP whose input is the 3D spatial location and the output is the 3D velocity. And then we jointly optimize both of these networks. So we have first a data fidelity loss, which says that the estimated emissivity should agree with the observed video when we project it onto the image plane. We have velocity regularization, which is enforcing a theoretical velocity model onto the estimated emissivity, onto the estimated velocity. And this is a sort of way to guide the estimated velocity towards something reasonable. And then we have a dynamics loss that connects both of these networks. So it says that whatever velocity we've estimated, it should agree with the dynamics of the estimated emissivity. So this work can be seen as a generalization of a previous method known as BH-NeRF. And this method was actually used to do the first ever 3D recovery of a flare around a black hole, Sagittarius A star, from real data. But there were specific assumptions that were held in that scenario, but don't hold in general. So the way that BH-NeRF works is that it assumes a fixed Keplerian velocity field. So it only estimates the initial 3D emissivity, and then it propagates that according to Keplerian orbital dynamics, which is pretty constraining. And so it only worked in this scenario because there was just a single flare that was far enough away from the black hole that it could be approximated as following an orbital, as a Keplerian velocity model. And there was just a single flare happening in the first time frame, and there were no further flares that occurred during the observation time window. Whereas in our scenario, so the drawback here is that when you have a fixed velocity model, that can bring in inaccuracies as we get closer to the black hole, where we start to see things like matter infalling towards the black hole. So we have negative radial velocity. We start to see things like turbulence and sub-Keplerian velocities. And then also when you only estimate the initial condition, that doesn't let you recover new emissions or flares that might happen after you start observing. Whereas with our approach, we jointly learn the velocity field, which allows us to overcome any errors in the assumed velocity model, because we're only enforcing that now as a soft constraint. And then since we're approximating the emissivity field using a 4D time-dependent MLP, then we can actually recover new flares that occur over the entire time window of observation. So I wanted to share some preliminary results on simulated data. So for this example, we simulated some hotspots moving around a black hole according to a predefined velocity model. And then these would be the image plane measurements observed from the EHT's point of view on Earth. And the goal is to reconstruct the emissivity field at the beginning. So here's a reconstruction using BH-NeRF. And the reason that it looks so messy is because the velocity model was incorrect. So if we take a look at the ground truth velocity in the equatorial plane, which is also the plane on which the emission is orbiting, we can see that there's some negative radial velocity corresponding to matter infalling towards the black hole. And there's also a certain angular velocity profile where the velocity increases as we get closer to the black hole. But with BH-NeRF, it assumes a fixed Keplerian velocity model, which imposes 0 radial velocity everywhere and also has a slightly different angular velocity profile. So that's why the reconstruction of the emissivity also looks more messy, because the velocity just wasn't correct. Whereas with our approach, we get a much cleaner reconstruction of the emissivity, and the primary reason is that we jointly reconstruct the velocity field, which is much closer to the ground truth. So we do recover this negative radial velocity area, and we also recover a more accurate angular velocity field. And I guess it's interesting to note that it becomes less accurate at small radius and at high radius, which corresponds to a region where we have less emission signal coming from the data. Okay, so that wraps up our talk, our discussion on 4D black hole emission tomography. Yes, question.
So your like velocity components are being evaluated against some sort of model you're running at the same time, right? Or in this case, you have a ground truth velocity data, right?
Yeah, we actually simulated it according to our own predefined velocity.
Did you also, or did you try like a pin type thing to like try and weakly enforce like satisfying the GRMHD equations or something like that with your reconstructed velocity field?
That's a good question. We did not try that. So actually for our velocity field, we didn't use a GRMHD equation. We just used like a kind of a simpler velocity model. But it would be cool to incorporate like GRMHD equations.
Or even
Yeah.
just like to satisfy whatever equations you use there.
Yeah. So
Seems like a good use case for a pin, I guess is what I'm saying.
yeah, I think we did. I guess you could sort of impose it here in the velocity regularization for the. So for us, it was just like a theoretical velocity model that could be defined on sort of this like 3D grid. But maybe, yeah, for a GRMHD equation, it'd be kind of harder to formulate it in that way. So yeah, that would be more like a pin loss then. But we haven't tried that yet.
Okay, thanks.
Yeah. Okay, gonna go ahead. All right. Any other questions about that part? Okay. So now I want to talk about our recent work on how to add general physics constraints onto generative models. And this is a way to kind of merge the two paradigms of data-driven and physics-based priors, so that ultimately we want to be able to have the flexibility and the expressivity of data-driven priors, but still the reliability of physics knowledge, right? So by now, I'm sure, well, I hope that you're convinced that diffusion models are great for visual quality. So I've been showing these images of GRMHD simulations, and these are some examples of generated samples coming from a diffusion model that was trained on GRMHD images. These look a lot like training samples, so it would be hard to distinguish these two different sets, right? But what if I told you that there was a constraint underlying all of the training samples, which theoretically the diffusion model should have picked up on as well? And it was a very simple constraint. It was just that all of the training images had the same total brightness, meaning that all of the pixel values summed to the same number, which in this case was 120. But it turns out that the generated samples don't satisfy this very simple constraint. So if I plot the histogram of total brightness generated by the diffusion model, I can see that it's giving me total brightnesses that are kind of spread far apart and not centered at the correct value of 120. So I'm going to show a way to incorporate such a constraint and even more complex constraints into the diffusion model so that we get something more like this, where we sample from the constraint satisfying diffusion model and get samples that more closely align with the true constraint. So we demonstrated this on the total brightness constraint as a simple example. We also looked at a 1D Burgers PDE constraint as the constraint that we wanted to enforce. And we looked at divergence-free constraints of Kolmogorov flows. We also looked at a geometric constraint enforcing periodicity in the image. And what's nice is that you can also use a black box constraint. So for this, we looked at like a semantic constraint constraining the exact number of galaxies present in an image. So we trained a CNN to do the counting for us, and then wanted the images to fool the CNN to think that there were actually 8 galaxies in the image. So to illustrate how the method works, I just want to look at a simple 2D example. So let's say that we have a 2D data distribution represented by these gold stars. It's constrained in the sense that all of the samples lie on a constraint manifold M. And so if I train a diffusion model on these samples, I would hope that it also satisfies the constraint. But in practice, due to learning errors and sampling errors, I can easily get samples that fall off of the constraint manifold and therefore violate the constraint. So there was previous work that proposed a neat solution to this called mirror diffusion models, where the idea is that you can map the constrained space into an unconstrained space via something known as a mirror map. And then there exists an inverse mirror map that takes any point in your unconstrained space, namely all of RD, and then maps it back to the constraint manifold. So then you can train your diffusion model in the mirror space, and any samples from it will get automatically mapped back to the constrained space via the inverse mirror map. So this is a really neat idea. Unfortunately, analytical mirror maps only exist for convex constraints, meaning that the constraint manifold is defined by a convex constraint set. And in general, it's hard to derive analytical mirror maps and their inverses. So we wanted a way to tackle arbitrary constraints, even non-convex ones, as might arise in many physics applications. And for that, we proposed replacing the analytical mirror maps with neural networks, where we have a forward mirror map with parameters phi, so g phi, and then we have an inverse mirror map f psi. And then once we've trained both of these mirror map networks, we can follow the exact same framework as before, where we train the diffusion model or any other generative model for that matter in the learned mirror space, and then have its samples automatically mapped back to the constraint space via the learned inverse mirror map. So the exact objective function looks a little bit like this. So we jointly optimize both of these networks' parameters, and we have a cycle consistency loss, which encourages both of the networks to be inverses of each other. We have a constraint satisfaction loss, which encourages the inverse mirror map to actually map back to the constraint set. And finally, we have a regularizer, which ensures a unique solution. So for our experiments, we just assumed that G, the forward mirror map, should be as close to the identity map as possible. So an application that I'm really excited about is using this as a way to obtain physics-constrained, data-driven priors to solve inverse problems in the sciences. So one simple inverse problem we looked at was, let's say that you observe two noisy states of a Kolmogorov flow and you want to infer the missing states. We can recast this as an imaging problem of denoising and then in-painting if you train like an image diffusion model on Kolmogorov flows, right? And then we can just plug that diffusion model into an off-the-shelf diffusion-based inverse solver to solve this inverse problem. So that's exactly what we did for the baseline approach. So we use something called DPS, which is an inverse solver that takes a pre-trained diffusion model and solves the inverse problem. And you can see that it gives us this kind of in-painted vorticity field that looks visually plausible. But then if we plot the divergence field of the solution, we can see that the divergence is far from zero. Whereas with our approach, our diffusion model now satisfies the divergence-free constraint. And so we get a vorticity field that visually looks very similar to the baseline reconstruction. But in terms of the divergence, it's much closer to zero, meaning that our solution is more physically plausible under this constraint. Okay, so that wraps up the part about kind of merging physics-based and AI or data-driven based approaches. And just to sum up, we've looked at a variety of problems along this spectrum of increasing imaging complexity and therefore the strength of the imaging assumptions that are needed. And so to solve these increasingly ill-posed challenges, specifically in black hole imaging, we had to go from using data-driven priors to physics-based priors. And then I also proposed a way to incorporate arbitrary constraints into the generative model itself. So now I want to touch on some ideas for future directions of research that I'm interested in. So I want to really push this idea of going beyond imaging under a single prior, which has sort of been the de facto framework of computational imaging, and really pitch imaging under multiple priors. Because when you have limited data, no matter what prior you use, the image you get out is very likely not a reflection of the way the thing actually looks in real life. And so to mitigate the bias that comes from using a prior, we have to look at reconstructions under a variety of priors so that we understand what parts of the image are coming from prior assumptions versus what parts of the image are coming from the real data. So the work I did on black hole imaging provides like a very simple example of this, where we imaged M87 under a variety of priors, and that allowed us to tease out which parts of the images were reliable and which parts were more reserved for the imagination, right? So it looks like the diameter of the ring is prior invariant, so that's a reliable feature, whereas the thickness or the thinness of the ring itself depends on the prior. So we probably don't want to overinterpret that part of the image. And so there are questions about how do we rigorously kind of define the so-called meta posterior of different priors. And I would love to be able to then disentangle image features as coming from the measurements versus coming from the prior. And of course, there are some technical challenges associated with how do we scalably infer this many posteriors when it's already so expensive to generate training data for a single diffusion model and then train that diffusion model and then infer a posterior under that single diffusion model. And now we want to do this for multiple priors. Well, how do we scale that up? So another way to responsibly harness the bias of AI priors is to make sure that the AI priors themselves are more reliable. And a way to do that is to incorporate physics knowledge, sort of in the spirit of the mirror map approach that I just talked about. So here's a video that Sora gave me when I asked it to give me a video of a steaming cup of coffee. And if you take a close look at the steam, I would guess that that's not actually satisfying like a very rigorous fluid flow PDE or whatever. And so how do we incorporate such a constraint into generative models to, first of all, make them more accurate by satisfying obvious physics principles, and also make them more data efficient Because right now the hope is that if we just train these models on enough data, it'll just naturally learn the correct physics. Well, we can surpass the need for all of that data if we just go ahead and put in the physics knowledge we want ourselves. And finally, kind of the ultimate goal as an imaging researcher myself is to have imaging enable new scientific discoveries. So a step towards that is building more physics-based imaging approaches as a means to allowing us to better learn physics. So very simple example of that was through the black hole emission tomography work, where we jointly reconstructed the physics model, i.e. the velocity model, which allowed us to refine our understanding of the way particles move near a black hole. So it allowed us to deviate from our theoretical assumptions and recover modified models that fit the data better. And then also when we use physics-based approaches, I think because we're incorporating extra assumptions coming from physics, that will allow us to tackle more and more ill-posed problems, which ultimately will let us just image more scientific phenomena. So I'm also just interested in tackling a lot of the remaining open problems out there in the sciences of things that we haven't been able to visualize before, like the surface of an exoplanet, or more accurate reconstruction using cryo-EM methods. If we can go ahead and image these phenomena in the first place, then that will enable more understanding of them and also motivate more interest in studying these phenomena. Okay, so with that, I want to thank my collaborators involved in all of the projects that I've talked about. So these involve computational imaging people, astrophysicists, and also some material science people.
Other questions for Berthy?
Well, thanks for the nice talk. Instead of using varying your priors, have you thought about just using an uninformative prior, something like Jeffrey's prior or
An uninformative prior. Yeah, I mean, but then the question is like, then what's the point of using a prior?
but if you believe that your priors are affecting your actual posterior in a way that you don't want it to, instead of
Yeah.
varying your priors, whatever. I don't know. What do you see as the advantage of either approach?
So, yeah. So with imaging, I think there are merits to actually imaging under a stronger prior so that the image becomes more interpretable to humans, because ultimately the way a lot of us process information is through visual data and through like human interpretable images. And for that, a lot of times you do need to use a stronger prior to get something that actually looks like a natural image. And then I think the philosophy of our work in using multiple strong priors rather than a single uninformative prior is that then we allow people to choose which prior they most believe in. So it's not like you're stuck with a single meh prior. It's more like you have a bunch of good priors to choose from. Which one do you most believe? And then if you really believe the strong prior that you've used, then you can go ahead and make more conclusions from that. Whereas if you start out, I feel like if you start out with an uninformative prior, then that's where it all ends. Like, what else do you do after that once you get the image out? It doesn't really look like anything beyond the data that you started with.
Right. That's
Yeah.
fair enough.
Yeah, thanks for the nice talk. I have a very broad question. Could you comment a bit more on the scientific impact on this work? Like, was there like specific learnings from like doing all of this about like astrophysics, about the properties of black holes in general? I think you
Yeah.
commented here and there a bit on like
Yeah.
the learnings. Could you just like give like some more details there?
Yeah, so specifically for the M87 work, we actually quantified kind of like uncertainty bars around the features of the image. So we kind of fit a ring model to the image and then like looked at the diameter, the fractional width, and the brightness contrast of the black hole. And yeah, so that's kind of like probably the most scientific thing that we did as a result of the imaging. But I do think that the holy grail of imaging is to be able to discover something new, which I'm not aware of if anyone's been able to do that before, but like that would be really cool, right? Yeah.
Thanks.
Yeah.
Yeah, thanks for a great talk. I guess my question goes back. So you, in this case, were holding the models constant. This is going back to the different priors and then changing the prior. Is there any reason to think that changing what types of models you're using, kind of that interplay between priors and different models could also play a factor as to what we're viewing as more or less likely? Or do you think you can just abstract it purely to, you know, how well you're matching a likelihood? Or are there kind of many ways to match a likelihood, kind of from different perspectives of maybe what types of patterns a particular generative model is able to more easily reproduce?
Can you like rephrase it? Sorry,
Yeah,
can you rephrase
okay.
your question?
Let's say you take your whole setup,
Yeah.
but now I give you a different generative model
Okay.
and you use the same sort of training setup.
Yeah.
Do you expect it to change your answers?
A different generative model for the posterior or the prior?
Either or, yeah.
So I think so if you're given like a new prior, yeah, like definitely like the images will look different depending on like if you get like a new diffusion model prior and you want to plug that in. Sorry, I
I'm
think
not changing
again,
the
not
prior, it's
really.
just really the network architecture. Yeah, can someone translate?
Oh,
Okay.
oh, I guess
So I
I'm
mean
thinking of
specifically for
generative model.
whatever learned functions you have.
So like how much does this depend on the architecture of the models? Okay, yeah. Okay, I understand your question now. Thank you.
Maybe yeah.
Yeah.
So which part of it could I have been asking about?
Yeah. No, I think
No, the
I think I understand your question now. Okay, so the question is like, I guess like what if in the variational inference setup, like what if I instead of using a diffusion model, I use like a VAE or like a GAN or something? Gotcha. Yeah. So yeah, that is definitely something that's going to change the first of all like the inductive bias of the generative model, how easy it is to actually compute that log probability function. So that is something that we haven't looked into yet, is like how the model architecture changes the bias of your prior. Because yeah, like the framework that we're proposing now all operates under the assumption of your prior is perfect. And it's like the model has perfectly learned the training data distribution. But obviously these priors are not perfectly learning the training data distribution. Yeah, thank you. Yeah, thank you.
Other questions for Berthy? I wanted to ask about the mirror mapping, actually.
Yeah.
So it's a learned mapping, right?
Yeah.
I wanted to ask, is there reason to believe when you apply the mirror mapping after you learn that transformation that it will only apply the constraint that you're hoping to satisfy and will modify the sample in no other way?
Oh,
Is that
yeah.
something I should be concerned about?
So that theoretically should be handled by that cycle consistency loss, where without the constraint loss, it's just going to reproduce the training samples. Yeah, so that cycle consistency loss should mitigate that fear. Approximately. Yeah. So there's going to be like a little bit of distribution shift probably when you look at what happens when you compare like the training data versus training data pushed forward through the forward mirror map and then pushed backward through the inverse mirror map. It's going to have a little bit of shift. Yeah. But we actually looked at, so we did some experiments where we evaluated like FID and like MMD, like basically like distribution matching metrics of like a vanilla diffusion model trained directly on the training data versus our approach of like training a diffusion model in the learned mirror space and then mapping it back through the inverse mirror map. And we actually got lower FID scores and MMD scores than if you were to just like directly use a vanilla diffusion model. Yeah.
So regarding the mirror map, like I'm not sure if I understood. Is the idea that you learn to go to like an unconstrained space where you can train your model like in like the classical way, and then when you go back, it's as if you had trained your model with those constraints, or
Yeah.
yeah.
It's a way of like basically like modify like putting your training data in a new space so that it's easier for the diffusion model to learn both the data distribution and like the constraint. Yeah. Answer your question.
Okay. And then like you sample from your model, and then you have to apply like the inverse. Transformation.
Yes. Yeah. But like once you've moved your training data into the mirror space, you can train your diffusion model as normal in the mirror space.
Okay, that makes sense. Yeah.
Last call. Okay, let's thank Berthy again.
Okay. Thank you.